Now let us see the path. So what is the path? If suppose we have an equilibrium state of a system, and from that state we want to go to another state, so we can do that by many different kinds of paths. So while studying the transition, understanding that path will be important. Let's say we have this is state A, equilibrium state of the, and this is state B. Now we can let us consider these. For example, uh, state A is 3 moles of H2 gas, pressure is 5 bar, and temperature is 100 degrees Celsius. Now this is state A, equilibrium state A. Now to go to another state B, the other state is um, same 3 moles of H2 gas phase, and but pressure is 1 bar and temperature is 50 degrees Celsius. So now we have went from equilibrium state A to equilibrium state B. So how many ways means there are infinite number of ways how we can go from A to B. So one path could be constant pressure path initially. Like initially pressure is kept constant and temperature sorry volume is reduced initially. Assume these are straight. So we can rather consider this as temperature. So temperature initially it was 100 degrees Celsius, and this state B is 50 degrees Celsius. And here we have to see the pressure. Initial pressure was at state A it is 5 bar, and here it is 1 bar. So the first path would be constant pressure, that is pressure is put at 5 bar and temperature is reduced from 100 degrees Celsius to 50 degrees Celsius. So that gives us then once we got to 50 degrees Celsius, then we can put the temperature constant at 50 degrees Celsius and um, reduce the pressure to 1 bar. This is one path. Or we can also take another path, that is initially putting temperature constant at 100 degrees Celsius and reducing the pressure to 1 bar, and then putting the pressure constant at 1 bar and then decreasing the temperature. So this is another path. So we have two different paths. We can also do this by keeping the system in equilibrium all the time. So for example this path here, so at each point the pressure and temperature are in equilibrium with the system as we go from A to B. So the temperature and pressure are decreased in extreme infinitely small amount. So That's how this is reduced. So basically, it is a slow and steady transition. Now, there are three different types of paths. So, first path is reversible path. Basically, a path where the system can be returned to its original state without any change in the surroundings. So, that is a reversible path. Um, for example, if we take a container with gas inside and we have a piston. Now, if we move the piston very slowly with a very small amount of force, like df is the small amount of pressure basically applied on the dp is the small amount of pressure applied on this piston, then the piston moves very slowly and the system stays in equilibrium all the time, and this is the reversible path because at any time we can bring back the original state by reversing the uh, process that we are doing. Now, in case if the piston is suddenly applied a significant high amount of pressure on this piston, then in that case it will be irreversible path, and that process is a irreversible process where the system cannot return to its original state without a net change. There is also another path which is called adiabatic path. So this is a reversible path and this is irreversible path. And in the case of adiabatic um, path, we insulate the system with the thermal insulation so that there will be no heat exchange. No heat exchange with surroundings. That process is called adiabatic process. So this is all about path, and it is very important in order to understand the system. So then only we can tell about amount of as the path influences the heat energy flow with the surroundings, that is heat exchange. Also it will determine the amount of work done by the system on surroundings or surroundings on the system. So that is determined by the path. Hence understanding the path is very important while solving the problems. Next, let us look at this isobaric and so basically isobaric process. This is a constant pressure process. So in this case, the pressure will be constant during this path. So here it will be. Um, so we have a state A, and oh, this is how we reach. It happens at a constant pressure. So the pressure remains same throughout the process, uh, and it is called isobaric process. Whereas other properties such as volume and temperature may change, but pressure remains constant. And this is extremely these definitions are extremely important for us, because in the question if it is mentioned isobaric process, so you should understand that the pressure is constant throughout the path. So if it is a isobaric process, pressure is constant, and what will be the dp in that will be 0. We also have isothermal process, where let's take a point. Sorry, this can't be volume. Rather, it is. This is all always volume and temperature would be on the x-axis mostly. That's the usual way of putting. So this is a constant state here. Assume that this is straight line, even though my drawing is not fair. So it is happening at a constant temperature. This is a constant temperature process. So P comma V may change, but T is constant throughout the process. So that's basically isothermal process. Now let us consider zeroth law of thermodynamics. So here we have. So what does zeroth law of thermodynamics tell? Basically, in the first lecture we have seen it defines the concept of temperature. So how does it define the concept of temperature? So in thermodynamics, for us, temperature is something more important when we characterize a system. Um, Other state variables also important, but nevertheless, it has its own implications with temperature. So we have three bodies here: A, B, and C. Now we have joined A with C and C with B here. So and these A, B, C, these three systems are in equilibrium. A, B, C. These are the three systems. Now here A comma C are in equilibrium because they are connected or joined as shown here. So these are in equilibrium, then we can write a function with state variables. There could be, I mean, generally pressure, volume, temperature, or the state variables, but I'm just indicating them as A1, A2, A3 so that they are the state variables of system A. But pressure, volume, temperature, number of moles, not just these are the state variables of a system, but these are predominantly we use because they are significant or more. But there could be other state variables also, like length or whatever for a system, length or density, and so on. Um, yeah, and there could be so on, and similarly, sorry. We have similarly for C1, C2, C3, so on, and this function equals to 0. Because A and C are in equilibrium, we can write a function like that. Basically, so this will reduce to theta A is equal to theta C. In fact, theta A and theta C are function of their state variables. Let me write theta A of A1, A2, and so on AN equal to theta C of C1, C2, so on Cn. So this is one equation that we can get. Similarly, as C and B are connected, B comma C are in equilibrium, and so we can write a function as similarly like B1, B2, B so on C1, C2, C3, so on equals to 0, and this will um, reduce to theta B of theta C of. So this is second equation, and from 1 and 2 we can conclude that theta A is equal to theta B, theta A of A1. So basically it shows that from 1 and 2 an here is equal to theta B of B1, B2, so on Bn. Hence, A and B are in equilibrium. So that's what zeroth law says. So what does it imply? It implies the concept of uh, so it implies the concept of thermometer and temperature. So here we have three bodies here. Now the B can be, or in fact C can be a thermometer. So using thermometer we want to determine the temperature. Means C can be used as a thermometer here, so that using that we can determine A and B are at same temperature or different temperature. Now with C, if something, a body, particular body A reads a value of temperature, and if we use the same C for measuring another body B, and if it is also uh, in equilibrium as in the case of previously, then A and B are at same temperature, or it can be used to measure the temperature variations. So yeah. Now we have ideal gas thermometer. So basically, compared to other thermometers, ideal gas thermometer is widely used at lab level or scientific research lab. Ideal gas thermometers are used where more precision is required. Now we have other thermometers also, like mercury thermometer, where as the temperature, as it takes more heat, then the mercury expands and we get a reading. So here in that case, the temperature is correlated with the expansion of mercury, and it is calibrated in that way. So that happens in the mercury thermometer. And also the scale that is used in mercury thermometer is linear scale. uh, so the same with the ideal gas thermometer, where uh, the scale is linear scale. Basically it's linear interpolation. And in the case of that mercury thermometer, which is a centigrade scale, where so basically that was centigrade, and where we have used the property of expansion of volume of mercury. But in the case of ideal gas thermometer, we are going to use the ideal gas property. Let me use another color. So this is ideal gas property. It uses. So the ideal gas property is that when we reduce the pressure and increase the volume, it just keeps on going, and at a point it just stays like this. At a very small pressure, it happens to be like this. That is, limit P tends to 0 or limit volume tends to infinity. So that happens in this region hereafter. So this region correspond to this thing. So it just stays like this. And after this, V tends to infinity, then PV is constant, is a constant. That is, it is no longer depends on pressure or volume. Then volume tends to infinity or pressure tends to 0. So PV is equal to constant, and it depends on the temperature. On temperature, its value depends on temperature. So now hereafter, whatever the this basically this curve is, what is the curve? That it is a PV curve, because we are plotting on the P and volume axis. It is a PV curve. So now here we are using the property that is being used here is limit P tends to 0 PV of an ideal gas, and this will give us the reading of temperature, because the temperature, because the this value depends on, this value is a function of temperature, is a function of temperature. And how we are going to measure the temperature means, so basically this is Kelvin scale we get. For with this thermometer we can measure up to 1 Kelvin or like that. But theoretically it defines 0 Kelvin. So how we are going to measure then we are multiplying this number with, there is a reason why we are doing this, because it is a triple point of water where water remains in all three phases at a particular pressure. This is a triple point of water where limit v tends to infinity. I'm writing I write usually LT for limit, but you can write LM. This is mostly used LIM. Um, PV of that ideal gas system divided by limit V tends to infinity at triple point. A triple point of water where water exists in liquid, solid, and ice form. So this will give us the temperature in Kelvin. So where does triple point of water happens? That is at a particular temperature and pressure, which is 273.16 Kelvin, and the pressure is 6.1 into 10 power minus 3 bar. At this temperature and at this pressure, the water the water will be in solid, liquid, and gas phase in equilibrium basically. So that's a important thing, in equilibrium. So this is the zeroth law of thermodynamics and lecture 2. In the lecture 3, we will see more concepts related to thermodynamics. Thank you so much for watching, and do subscribe.